Hello everybody, welcome back to my Gregorious Maths video. In this video we're going to be pressing on with homological algebra, and I'm going to be looking at projective modules. So disclaimer, if you don't know what a free module is, then look up the definition and then come back to this video, because I'm going to assume that you know what a free module is. Okay, so with that out of the way, let's just get into the video. So, I'm actually not going to begin with the definition of a projective module. I'm going to begin with a proposition, which looks very similar to the definition of a projective module. So the proposition is, given R modules M and N, and F, such that F is free, then this diagram commutes. So we're going to have F at the top, and then this is going to go via some G to N, and then this is going to go surjectively. Let me do the cool little double arrow thing. This is going to go, this is going to go surjectively via F, and now the proposition says that, and then we're just going to add a little zero in, because this F is surjective, and so the convention is to add a zero into this diagram, because then this row is exact by the surjectivity of F. And so the proposition is that there exists some H. Now it's not unique. Note that this is not unique. This is just a R module, R homomorphism H, such that this commutes. And yeah, F is a surjection. And they're all R homomorphisms, module homomorphism. Commutes. Sorry. Okay. So, let's give the proof. Alright, so, first of all, let's do this in black. Let X be the basis for F. Okay? And let's say X is in X. Now, let M sub X in M be the element such that F of Mx equals G of X. Then, by the property of free modules, there is a unique R module homomorphism H from F to M, which extends the function which maps X to Mx, and then the rest is clear. Okay, so now that from this it's pretty trivial. And so now that we have this out the way, let's define a projective module, and then I'm going to give a theorem which states a few equivalent conditions about projective modules. So, let's see. Sorry, not the theorem, this is a definition. My bad. Definition. We say that an R module P is projective if, and then given R modules M and M and N, the following diagram commutes, and then we're going to have, it's the exact same diagram like this, so we're going to have a map going down to N, and then we're going to have F going surjectively here. There exists some H like this, and this is just a convention because then we can say that this row is exact. And these are all R module homomorphisms, commutes. Alright, so now I'm going to use a whole new side of the board because this is basically the whole point of the video. So let's do this. So, there are a few equivalent conditions about projective modules, and I'm going to give a couple of them, I'm going to give 3 of them here. Alright, so, theorem. Alright, so, the following conditions are equivalent. So, first of all, P is projective. Secondly, the functor hom of P is exact. And 3, there exists an R module Q such that P direct sum Q is free. Okay? So these 3 conditions are equivalent, and again, there are more conditions which you can add to this list, but because I want to make this video somewhat concise, and these are pretty important ones, especially this hom one. This one is going to pop up later in the series, along with the injective modules and the analogous theorem about them and hom. Spoiler alert, by the way. So I'm just going to prove these 3 conditions. So let's see. So what colour should we do it in? I'll do it in. Actually, no. I'll do it in green. I'm feeling so happy. So blue doesn't seem appropriate for this proof. All right. So I'm going to give it a whole new side proof. So first of all, let's do this one. Well, this hom functor right here is left exact. So the covariant version is left exact, and so all we need to show is that this right here and then we're going to have composed F, because this is the induced map. Is surjective whenever F is surjective. But notice that because we're taking in an input from hom of PM, And right here, where is it? By the definition, there do exist such homomorphisms such that this is a surjection, such that this is a surjection. And so therefore, by the fact that P is projective, this right here is surjective, and therefore this covariant version of Hom is exact. So, hopefully that makes sense. And because P is projective, this function here is exact. Okay, so that was a nice one, but my favourite version is number 3. So I'm going to give it a whole new colour. I'll give it the black colour. Number 3, I like this one. So, let's do this. So, by this right here, if there exists an R module Q such that P direct sum Q is free, then by the first proposition we have that some F isomorphic to P plus Q, and then we're going to have maps going to P and then to N, and then we're going to have a unique one, H tilde, going to M, and then we're going to have this, let's say, going via F to N, and then again this is going to go to 0. And then this commutes. Right? And so, because this commutes, we can define a new function h such that this triangle here commutes as well. And how do we define it? Well, I'll leave it you two to check, but it's somewhat simple to check that defining h of p equal to h tilde of p0 makes p projective. Let's just say p is projective. So therefore, number 3 and number 1 are equivalent. So thank you for watching this video. Hopefully you get some of the fundamentals, at least, of projective modules. And hopefully I'll see you in the next video. Goodbye.